Okay, so suppose you are looking at the night sky and you're looking at some constellation in the sky. If you keep track of its position over the course of the night, what you'll find is that it's gradually moving across the sky, right? So uh, early in the evening, a constellation might be over here, but then later on, it might be higher up in the sky, and then later on, it might be further somewhere over here. And so you will see that the constellation or any constellation that you're looking at, or any star or anything that you're looking at in the sky, will gradually be changing position. And you will find that it moves from east to west, right? Um, Now, why does this happen? The reason that this happens is pretty obvious. It's because the Earth is spinning. So here is the Earth, and you are somewhere over here. Let's say you're over here, and so right. So this is the Earth. You're over here, and so the Earth is spinning. So your position is changing, but you can't tell that you're spinning. We can never tell that we are on a rotating Earth, and so we think we are at rest and everything else is moving. So to us it would seem that something up in the sky is changing position, but what's actually happening is that we are changing position. The Earth is rotating, and so that is why um, all the constellations in the sky seem to move from east to west, because the Earth rotates from west to east. Now, ancient astronomers, by that I just mean our ancestors, human beings who existed on the Earth many hundreds of or thousands of years before us, when they looked at the sky and saw this, to them it looked as if there was some kind of a celestial sphere or some giant sphere that was being rotated around the Earth. So they didn't know that the Earth is rotating. All they could tell is that the stuff in the skies, like the constellations, are moving across the sky like this, right? And so to them, it seemed like the entire Earth is surrounded by this giant sphere, right? And this sphere has all the constellations painted on it, and this sphere is rotating, and that is why the constellations move across the sky, right? So this sphere, which is completely fictitious, of course, this sphere is called the celestial sphere. So to the ancients, it appeared as if the stars must be firmly attached to a celestial sphere. And of course, let me emphasize here that this celestial sphere is completely imaginary. It's just this, it seemed to them as if all the stars and constellations are painted on this sphere, which is being rotated around the Earth. So it's like an astronomical painting on a heavenly ceiling. So, so they would see that all these stars and constellations they would see that all these stars and constellations seem to be rotating, right? But what if they looked at a star which is directly above the North Pole, right? Is there a star directly above the North Pole? The answer is yes. That star is called Polaris. So that the star Polaris happens to be located directly above, directly above the North Pole. In other words, if you were to draw a line from the south to the North Pole, imaginary line from the south to the North Pole, that would be the axis of the Earth, right? The axis is just this imaginary line around which the Earth is spinning. So the axis would be this line. So this is the globe. The axis would be this line joining the north and part of which joins the North and the South poles. And so the star Polaris happens to be located very close to the axis of the Earth's rotation. Now, if you were keeping your eye on the star Polaris, would the star Polaris rotate? The answer is no, because the star Polaris is directly on the axis, right? So as the Earth rotates, this particular star will not appear to change position. Every other star will appear to change position, right? So, so if you keep your eye on the different stars and constellations, and you happen to be in the North Pole, and you keep your eye on the different stars and constellations at night, they will all seem to be going around except for the star Polaris, which will remain fixed. And please make sure you understand why Polaris would remain fixed. Polaris happens to lie on the axis of the Earth's rotation. So Polaris happens to be at more or less at this location, very, very far away, of course, but at this location. And so as the Earth spins, this is the one star that does not seem to change position, right? So you can actually observe this. It's really, really fascinating. So I'll just show you a quick video of this, and let me optimize for video clip. All right, so I'll just show you a quick video of this. Okay, so what this person has done is they have pointed their camera towards the sky, right? Part of the sky where they can see Polaris, and they've used a long exposure. Okay, so I'll just let you watch this video, and then I'll explain some more. So if you keep your eye on this location, I don't know if you can see my mouse, but if you keep your eye over here, around over here, you'll be able to see the star Polaris, which is the only star that is not rotating. So basically what this person has done, as I was saying, was that he's kept his camera pointed in the same direction so that he can see these stars near Polaris. And so and then he's taken this video and he's sped it up. So now you can actually see that the stars appear to be going around in circles. So just watch that. So hopefully it's clear to you that the stars appear to go around in circles around the one star Polaris, which does not change position. And hopefully the reason for that is clear. It's because the star Polaris lies very close to the axis of rotation of the Earth. And so that is the one star that does not seem to change position. All the other ones seem to go around, and that is because the Earth is spinning. All right. He does a little bit more. He creates these amazing star trails. So I'll let you watch that for a moment. So what he's done here is that he's stacked all the individual photos that he's taken, and so they're all visible, and so you can see the paths traced out by the stars, and so these are called star trails. And so this is an amazing example of that. If you look on YouTube, there's many other videos like this. All right. Okay. Now, so it's clear that the Earth is rotating. That's something you already knew, that the Earth is rotating. The rotation axis is something that we'll often talk about. And I've already told you what the rotation axis is. If you consider this imaginary line, which joins the north and the south pole of the Earth, right, and extends out, that imaginary line would be the line around which the Earth is rotating. And so that line is called the axis of the Earth. So the axis is the imaginary line joining the north and the south poles. So in this diagram, this would be the axis. It goes through the Earth, comes out at the south pole. So this is the axis, or the imaginary line around which the Earth is rotating. Now, as you know, the Earth rotates from west to east. Another way of saying that is that if you were to look down on the Earth from above the North Pole, so suppose you're hovering above the North Pole and you're looking down on the Earth, then to you it would look like the Earth is spinning in the counterclockwise direction, right? So just imagine that you're up here and you're looking down on the Earth. To you, it would look like the Earth is spinning in the counterclockwise direction. So that's the same thing as saying that the Earth rotates from west to east, and that is the reason why the sun rises in the east and sets in the west. Okay. Um, the rotation speed at the equator is 1670 kilometers per hour. So if you are standing somewhere over here, like if you're standing at the equator over here, you are rotating with the Earth, right? So what speed are you rotating at? You are actually rotating at a phenomenally high speed. So you're moving with the Earth at a phenomenally high speed. And that speed is 1670 kilometers per hour, which is about 1037 miles per hour. That is much, much faster than a rifle bullet. A bullet typically travels at something like 200 to 300 miles per hour. So if you were standing at the equator, you would be rotating with the Earth at this phenomenally high speed. We don't live at on the equator in Nashville, so we live somewhere around here. So at the location of Nashville, um, the speed of rotation of the Earth is 1100 kilometers per hour, which is something like 600-700 miles per hour. So that too is really, really fast. So you might wonder, why is the speed at Nashville different than the speed at the equator? And that's easy to understand. That's simply because the Earth is spinning as a whole, right? So if a point is at the equator, it has to cover a much larger distance around to get back over here, whereas at a point that's at the latitude of Nashville somewhere over here just only has to cover a smaller circle to get back, right? So the circle that you're tracing out if you're in Nashville is smaller than the circle that you would be tracing out if you were at the equator. And so your speed is faster at the equator than it is at any other latitude. And so yeah, so you can see that we are spinning with the Earth at phenomenally high speed because the Earth is rotating pretty fast. However, we cannot tell that at all. So you cannot tell right now that you are moving together with the Earth at a speed of 1100 kilometers per hour. We really can't tell that because we don't know any different. To us, we can't even tell that we are moving. All right. Now, how much time does the Earth take to spin once on its axis? Think about this question for a moment. So how much time does the Earth take to go around once on its axis, right? So to spin around once on its axis, one spin. What do you think? You might say 12 hours, right? That is not strictly correct. Actually, the Earth takes a little less than 12 hours. It actually takes, sorry, you might say 24 hours. I don't know why I said 12 hours. You wouldn't say 12 hours. So you might say 24 hours, right, is the time taken for the Earth to spin once on its axis. But that is not strictly correct, right? In reality, the Earth takes a little less than 24 hours. It takes 23 hours and 56 seconds to do one full spin on its axis, right? So then why do we say, why do we uh, say that noon to noon is 12 hours? So, so suppose, so noon is defined as the time when the sun is highest in the sky, right? So suppose you measure the time from when the sun is highest in the sky to the next day when the sun is highest in the sky again, that would be 12 hours, right? So why have we defined that to be 12 hours if the Earth really takes 23 hours and 50, that would be 24 hours, sorry. So I don't know why I'm getting 12 and 24 mixed up today. So noon to noon is 24 hours, right? Why is it 24 hours then? And why is it not 23 hours and 56 minutes? That goes into the difference between a solar day and a sidereal day. So let me just explain what this is. Now, the period from noon to noon is what we call a solar day. And that is our social concept of a day. And so a solar day is defined as the time elapsed between noon and noon the next day, right? And how would you define noon? Noon is defined as the time when the sun is highest in the sky. So that is noon. If you're at the equator, then so if you're over here at the equator, if you live on the equator right here, then if you point a stick directly towards the sun at the equator, then at noon, the rays of the sun would be directly in line with your stick. And so there would be no shadow of the stick at all. In fact, that is what happens at the equator. At noon, objects which are vertical don't have any shadows because the sun's rays are directly vertical. But if you happen to live not at the equator, but say at the location of Nashville, um, then at noon, the sun's rays would not be directly vertical, but the sun would be at the highest position in the sky that it ever reaches. So if you start your stopwatch at the instant that the sun is at the highest position in the sky, at whatever your location is, and then stop your stopwatch when the next day, when the sun is exactly at the same location, so you're measuring the time interval between noon to noon. That is called a solar day, right? And that has been defined to be 24 hours, right? So that's by design. That's been defined to be 24 hours. Now, as it turns out, this is not exactly the amount of time it takes for the sun to rotate on its axis once. Why is that? Let's try to understand that. So let's go back to the example of somebody who lives on the equator just for convenience. So let's say that they have this stick, which is indicated by this arrow. Just so please look at this third diagram for a moment, the bottom diagram. So we have a person who lives on the equator, and they have a stick which they're pointing directly towards the sun. So at noon, the rays of the sun will be completely vertical, and so the stick will not have any shadow, and so they'll know that, okay, now the stick is pointed directly towards the sun. So at that instant, they start their stopwatch, right? All right. Now they want to measure a solar day, which is the time it takes for the sun to be the sun to be in the same position in the sky again the next day, right? All right. Now, the Earth is going to rotate. So the stick was initially pointed like this, but then it would gradually rotate as the Earth is rotating. And then eventually it would get to this position where the stick is again pointed in the same direction, right? But is the stick pointed towards the sun? So notice that the stick has rotated by a full 360 degrees. It was like this. It went as the Earth rotated, the stick went all the way around and then came back 360 degrees. So it's pointed in the same direction. But is it pointed at the sun? The answer is no. Why? Because in the 24 hours or so that it took the Earth to rotate 360 degrees, the Earth has also moved in its has also changed position. So the Earth was originally over here, but now it's over here, right? And so at the center of the Earth, I mean, now it's over here. So that is why the stick is not pointed directly towards the sun, even though the Earth has rotated by 360 degrees, right? So as a result of that, we have to wait a little bit more for the Earth to rotate some more and point towards the sun again. And so we have to wait about 4 minutes more um, for the Earth to rotate some more, such that the stick is pointed directly towards the sun, right? So the time interval between the stick being pointed towards the sun on one day and being pointed towards the sun again on the next day happens to be a little longer than it takes the Earth to rotate by 360 degrees, right? And so that is why a solar day is different from the time it takes for the Earth to rotate once on its axis, which is called the sidereal day or sidereal day. I never remember what the correct pronunciation is. So the sidereal day is the time taken by the Earth to rotate by 360 degrees. And that happens to be 23 hours and 56 minutes, right? But hopefully it's clear to you why the time taken between noon and noon is 24 hours and not 23 hours and 56 minutes. The difference is because the Earth is moving in its orbit. So when the Earth has rotated by 360 degrees, the stick is pointed in the same direction as before, but that direction is not the direction of the sun anymore. So you have to wait for it to rotate a little bit more, wait for the Earth to rotate a little bit more, and in 4 more minutes, it will again be pointing towards the sun. And so that is why the sidereal day and the solar day are different from each other. So please make sure you understand this. Okay. All right. So, all right. So I have this animation over here. So I'll just show this animation, and hopefully this will make it a little bit clearer. So the stick is being rotated, and it's been rotated by 360 degrees. And you can see that the Earth is rotated 360 degrees, and the stick was not pointed towards the sun, right? So it needs to rotate a little bit more in order to be pointed towards the sun, right? And so that extra 4 minutes is what is the difference between the solar day and the sidereal day. And so I'll just show this to you one more time.
For just $67, you can.
So you can see that the Earth is moving in its orbit as it's rotating. And so by the time it finishes rotating 360 degrees, that is one sidereal day. That is a sidereal day. And that is 23 hours and 56 minutes, right? But you can see that after the Earth has rotated a full 360 degrees, a stick that was pointed towards the sun is now not pointed towards the sun. So it's not quite noon yet. So you have to wait for it to rotate a little bit more so that it's pointed towards the sun, and it will be noon. And so that extra bit of rotation that the Earth has to do in order to be, so that the stick can point towards the sun again, is what causes the difference between the solar day and the sidereal day. Now, where does this name sidereal come from, and what does it even mean? So sidereal means relative to the stars. So why do we say relative to the stars? The reason for that is the following. So the stars are very, 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 very far away from us, insanely, insanely far away from us. So when in the last class, we talked about the closest star to us, which is 4.5 light years away from us. And 1 light year, as we discussed, is 6 trillion miles. So the closest star is like 25 or so trillion miles away from us, right? So if you use a star as a reference, a very distant star as a reference, its position is more or less fixed in the sky. And so if the Earth, so suppose you were doing the same thing that we were doing, you have the stick which is now pointed towards the star instead of the sun, and you let the Earth rotate a little bit, rotate by 360 degrees. And so the Earth will also move in its, so the Earth is rotating and it also moves in its orbit. And now the stick is pointed in the same direction. The star over here is so incredibly far away that after 360 degrees, it's still pointed towards that star, right? So the distant stars are a good reference to use for direction. And that is why we say that the true reference, the true amount of time it takes the Earth to rotate by 360 degrees is also called the sidereal day, because it's relative to the distant stars, right? For the distant stars, you can ignore the fact that the Earth is also moving in its orbit. It doesn't make a difference because the star is so far away, it doesn't make a difference. So that is where the name sidereal comes from. That's not super important. What's very important for you to understand is why there is a difference between a solar day and a sidereal day, and hopefully this discussion makes that clear. All right. Here is an example of a question that I might ask on exams and quizzes. What is the difference between a solar day and a sidereal day? Just what we discussed. There's no trick here. Feel free to pause the video and see if you can answer this question. So the correct answer is yes. So the correct answer is this one. A sidereal day is the time taken by the Earth to rotate once on its axis with respect to the stars, and a solar day is the time it takes to rotate once with respect to the sun. So if you have a stick pointed towards the sun, um, then the time it takes for between the sun being in that position in the sky, or the stick pointing towards the sun, and the stick again pointing towards the sun in the next day. So the time it takes to rotate once with respect to the sun is the solar day, and the time it takes to rotate, the true amount of time it takes to rotate by 360 degrees is called the sidereal day. All right. Okay. Here's a straightforward question. Constellations appear to move across the sky at night because, again, feel free to pause the video and think about this. The correct answer is because the Earth is spinning on its axis. So we've discussed this. So I mentioned earlier how the Earth is spinning on its axis, as you know. So if you're anywhere on the Earth and looking up at the sky at some constellation, we can't tell that we are rotating. So the constellation or star will appear to be moving in the opposite direction. All right. All right. Now, you will have noticed that the constellations that you see are not always the same. They vary at different times of the year. So during the summer, you will be able to see more or less these constellations in the sky. So you'll be able to see Sagittarius, Capricorn, Scorpius, and so on. So these are the constellations that you'll be able to see in the sky if you look towards the south, right? But during the winter, you see completely different constellations. You see different, so you can, everything looks different during the winter. So you can see the Orion constellation very prominently. It's very prominent during the winter. And then you see all these other constellations in the diagram on the right. So why is it that at different times of the year, we see different constellations? Let's try to understand that. Well, that is because of the orbital motion of the Earth. So the Earth is not just spinning in place. So the Earth is not just rotating or spinning in place. The Earth also happens to be moving around the sun. It's in orbit around the sun, right? So let's talk a little bit about the orbital motion of the Earth. So first of all, the plane in which the Earth orbits, or in other words, the plane defined by the Earth's orbit. So just imagine the circle that's being traced out by the Earth. So that's the Earth's orbit, right? So if you just imagine this flat plane through that circle, then that flat plane is called the ecliptic plane. So this is a very important concept, and it's written here, but I'll just write it again: ecliptic plane. So we'll be referring to the ecliptic plane very often in this course. So what is the ecliptic plane? It is the plane of the Earth's orbit. So if you draw a plane through the Earth's orbit, then that plane is called the ecliptic plane. All right, so the orbital path, defines a flat plane called the ecliptic plane. Now, another thing that you'll notice is that as the Earth is rotating around the sun, is orbiting the sun, the axis of rotation of the Earth is tilted by 23.5 degrees from the line perpendicular to the ecliptic. So here is the line perpendicular to the ecliptic. So here is just some line that's perpendicular to the ecliptic plane. Now notice the Earth's axis. So the Earth's axis, once again, we've talked about that multiple times today. The Earth's axis is the imaginary line which joins the north and the south poles of the Earth, and it's the imaginary line around which the Earth is spinning, right? So the Earth's axis is actually tilted with respect to the line perpendicular to the ecliptic, and that the amount of that tilt, this angle right here, is 23.5 degrees, right? This tilt actually plays a very important role in our lives, which we'll see later on. So the axis of the Earth is tilted by 23.5 degrees from the line perpendicular to the ecliptic. All right. And one more thing you can notice um, about the Earth's orbit is that the direction in which the Earth orbits the Sun is the same direction in which it spins around its axis. So if you were to look down on the Earth from above the North Pole, I told you that the Earth would be appearing to be spinning in the counterclockwise direction, which means that if I look down from here, then I need to spin the Earth like this. That would be the correct direction in which the Earth is spinning, counterclockwise, looking down from above the North Pole. The same thing applies to the orbital motion of the Earth. So if you were to, let's say that you somehow magically transport yourself over here, this is your eye with which you're looking down on the sun from above the sun, above the ecliptic plane, you would see that the Earth is rotating in the counterclockwise direction in its orbit, right? So the Earth orbits the sun in the same direction in which it rotates around its axis. Now, you might wonder, why is this? Is this some kind of amazing coincidence? The answer is no. And we will talk a little bit about why this happens when we discuss the origin of the solar system in chapter 6. All right, so but for now, just remember this fact that the Earth orbits the sun in the same direction in which it rotates around its axis. All right. Okay, now what is the speed at which the Earth is orbiting the sun, right? Um, it's not difficult to calculate that speed at all. You know the distance between the Earth and the sun. There are no students in the class right now, but if there were any students, or if I were teaching this live, I would have immediately asked the class, what is the distance between the Earth and the sun? This is one of the very important numbers in this course. The distance between the Earth and the sun is defined as 1 astronomical unit, as we discussed in the last lecture. And that distance happens to be 93 million miles. So that's the average distance between the Earth and the sun, right? So you can find out how much time, you can find out the circumference of the orbit traced out by the Earth, right? You know how to find the circumference of a circle. It's just 2 pi r if you know the radius. So you can find out the circumference of the circle uh, traced out by the Earth if you assume that the Earth's orbit is circular. And then you know how much time it takes for the Earth to do one orbit around the sun. How much time does it take? Can you tell me? How much time does it take the Earth to do one full orbit around the sun? The answer is the Earth takes 24 hours, 365 days to do one full orbit around the sun, right? So you can do distance, which is the circumference, divided by time, which is 365 days, to find the speed at which the Earth is orbiting the sun. If you do that, you will find that it comes to 107,000 kilometers per hour. So that's insane. So it's approximately, if I remember correctly, that's about 68,000 miles per hour. So the Earth is zipping through space at a speed of 68,000 miles per hour, or 107,000 kilometers per hour. You can't tell that, but you are right now being on the Earth. You are actually zipping through space at 107,000 kilometers per hour. All right. Okay, so that is the orbital motion of the Earth. So coming back to our question over here, why does the sky look different at different times of the year? Can you answer that? Why does the sky look different? So why do we see different constellations in the sky now than we did 6 months ago during winter? The answer is because at different times of the year, the Earth is in different parts of the sky. Earth is in a different location of space. So we might right now be over here, right, where the Earth is shown in this diagram. But 6 months ago, we were probably over here. We were somewhere over here. And so we had a view of the stuff that could be seen from this location, the stars and constellations that could be seen from this location. But now that we've moved over here, we are seeing stuff that can be seen from this location, right? So that is why we have a different view of the sky uh, at different times of the year. All right. Now, the darkened hemisphere of the Earth, which means by darkened hemisphere, I simply mean the part of the Earth which is facing away from the sun. So suppose the sun is over here, right? My hand is the sun over here. Then this side would be the side that's facing the sun. And so this is the side that would be experiencing daytime. Whereas this side would be facing away from the sun. And so this is the darkened hemisphere. And this is the side that would not be able to see the sun and it would be experiencing nighttime, right? So daytime on this side, this is the sun facing side, and nighttime on this side. This is the darkened part, the darkened hemisphere. So the darkened hemisphere of the Earth, where it's nighttime, faces a slightly different direction every night, right? And that is because the Earth is moving in its orbit. So right now, when it's suppose the sun is to my left, so to my left means that direction. So suppose the sun is over here to my left, then the darkened hemisphere, which is this side, is now pointed in this direction. But in a few days, the Earth will have changed position and it will have moved somewhere over here, right? So now the darkened hemisphere would be pointed in this direction, a slightly different direction. So every night, the darkened hemisphere of the Earth faces a slightly different direction, right? Now, over the period of one night, you can't really tell that the Earth has changed position, but over weeks and months, you can tell that the Earth has definitely changed position because the view of the stars and constellations that you can see in the sky is different. And that is because the Earth has moved to a different vantage, right? Now, I'll explain that with this diagram over here. And I'll also show you an animation. So let's say that the Earth is right here. Currently, it's what month is it? Yeah, it's almost June. So let's say that the Earth is right here at position A, right? Okay, so that is where the Earth is in its orbit right now as we speak in May. So it's more or less over here. Now, the darkened hemisphere is right here. So somebody standing over here, looking up at the night sky, looking up at the sky at night, will see these constellations. So they'll see the constellations Sagittarius, Capricornus, Scorpio, and so on. So these are the constellations that will be visible to an observer right now, right? Okay. Now, 6 months from now, um, actually a few months from now in September, the Earth will be over here, right? Yeah, 3-4 months from now in September, the Earth will be over here at position B. So now the darkened hemisphere sort of points in this direction. And so a person who's looking up at the sky at night will see the constellation Pisces, right? And then in December, the darkened hemisphere is pointing in this direction. So a person looking up at the sky at night will see these constellations, Gemini, Cancer, and so on. And so hopefully it's clear to you that at different times of the year, you will see different constellations. And that is simply because the Earth happens to be at a different location in space, an entirely different location in space. All right. Now, you don't just see constellations in the night sky. Suppose this person, let's go back to location A, our person at location A, and I'll just clean up this diagram a little bit. Let's go back to location A, and our person is now looking up at the sky. But let's say our person can't sleep that night at all, and so he or she just stays up until it's morning, almost morning, and the sun is about to rise. So then their location has changed. So the Earth has rotated, and now they're about to experience sunrise. So suppose they look towards the eastern horizon, right, where the sun is about to rise. So the sun has not risen yet. and that's why you can still see the sky, the stars on the eastern horizon. What constellations will they see on the eastern horizon when the sun is about to rise? The answer is they would be seeing these constellations, the ones over here. So Gemini, Cancer, so these guys, right? So then they're staring towards the east and they see the sunrise, and so they will see the sun rising in the constellation, in the part of the sky that has the constellation Gemini, Cancer, and so on, right? All right, suppose they do the same thing over here. So in September they do the same thing. So they wait till it's about to be sunrise. So they're in this location right now. The sun is about to rise for them, and just before sunrise they notice the constellations in the eastern sky. So so what constellations are they going to see? So they're going to be looking in this direction, and they will see these constellations, Virgo, Leo, and so on, right? And so they will say that, okay, in September the sun rises in the part of the sky where you have the constellations Virgo, Leo, and so on. And let's do one more. In December, suppose they're doing the same thing. They're really interested in which constellations the sun rises in. So in December, they stay up right till before sunrise, and they look in the eastern direction where the sun is about to rise. And what they find is these constellations, these guys, Sagittarius, Scorpio, and so on. So these are the constellations that seem to these are these are the constellations that are in the sky at the location where the sun is rising, right? Now this had been this is something that ancient people took a lot of interest in, so particularly in the West. So they were really curious about which constellations of the sky the sun rises in at different times of the year. And so if you do this every month of the year, right, I just did 3 of them, but suppose you do this every month of the year, then you will see the sun rising in all of these constellations that are indicated over here, right, in the outer circle. So the sun would seem to pass through, would rise through each of these, rise in each of these constellations at different times of the year. So these 12 constellations through which the sun passes, or in other words, the sun seems to rise uh, throughout the year, were called the zodiac. So these 12 constellations constitute the zodiac, right? We discussed how there are 88 constellations covering the entire sky, but these 12 are called the zodiac, and that is because the sun appears to rise in these constellations at different times of the year. And hopefully it is clear to you why the sun rises in these constellations, and it's just because of where the earth is, right? All right, so let me show you an animation of this. And I hope this animation works on my iPad. Okay, it doesn't work on my iPad, but I'll just open it on my computer and I'll see if I can show you. Oh, it does work on the iPad. All right, that's great. So let's do this. Okay, is it doing anything? Yeah, I guess it's not going to work on the iPad. All right, so let me just open this on my computer, and you can open it on your computer too and play around with it. Okay, let me share my screen. All right, so I hope I can open it over here. All right, now let's hope it works. Ah, there it is. So So this is what I was trying to show you with my hand-drawn diagrams. So a person who's looking at the sky just as the sun rises, just before the sun rises. You know, once the sun rises, you can't really see anything in the eastern sky. It's too bright. But if you're looking at the sky just before the sun rises, they will be seeing these constellations. And so they will be saying that the sun rises at in the part of the sky which has these constellations. And so let's just pause it. So in March, they would say that the sun is rising in the part of the sky which has the constellation Aquarius. And in June, they would say that the sun rises in the part of the sky that has the constellation Taurus, and so on. And so they had picturesque ways of referring to this. They would say that the sun has moved to the house of Taurus, or the sun has moved to the house of Gemini, and so on. And this was considered to have some important significance in our lives, but that is astrology. And I've mentioned that astrology is just a complete bunch of nonsense. It doesn't have any kind of scientific basis at all. It's just make believe. So, but hopefully it's clear to you why uh, where these beliefs come from. So, and it's clear to you why the sun appears to rise in the part of the sky which has these particular constellations. And as you can see from this simulation, it all has to do with our vantage, where we are relative to the sun. And so that is why the sun seems to pass through all these constellations over a course of a year. Okay. Let me just go back to my iPad. All right. Now, so we talked about the motion of the Earth around the sun, right? I'll just briefly mention something which we are not going to discuss very much in this course at all. This is stuff that's covered in the next part of this course, Astronomy 2. So we know that the sun is a part of the Milky Way galaxy. So here is a diagram of the Milky Way galaxy. And I mentioned in the last class that the sun is located somewhere off to the side. The distance from so you can see that the sun is located, um, the diagram indicates where the sun is located. It's located over here. So that is around 27,000 light years from the center of the Milky Way galaxy, right? The sun happens to be orbiting the center of the Milky Way galaxy, and it takes 230 million years to complete one full orbit around the center of the Milky Way galaxy. 230 million years. So now that's not all that the sun is doing. The sun is also, it also has a random motion. So the stars in the Milky Way galaxies, all galaxy, are not just uniformly rotating, right? They also have random motions with respect to each other. Um, so the sun in uh, in addition to the motion around the Milky Way galaxy, the center of the Milky Way galaxy, the sun has random velocities of 70,000 kilometers per hour. Um, so if you just look at some of the stars near the sun, you will find that all these stars, including the sun, they're not just uh, uniformly moving, they all have random motions with respect to each other as well. And so the sun has a typical speed of 70,000 kilometers per hour relative to other stars in its neighborhood. All right. 70,000 kilometers per hour is 40,000 miles per hour. All right, so that's very, very, very fast because, as I mentioned, a bullet from a gun has a speed of around 200 to 300 miles per hour. All right, now let me ask you this question. What causes the Earth's seasons? And feel free to pause the video and see if you can answer this question, or if you know the answer to this question. Okay, so a lot of people think that the correct answer is this. Um, the Earth moves closer or further from the sun, or in other words, the distance between the Earth and the sun is what causes seasons. But that is not the correct answer. The correct answer is the tilt of the rotation axis of the Earth. So I'd already mentioned this a little while ago. So I discussed how we talked about what is the ecliptic plane. And I told you that if you consider this imaginary line, which is perpendicular to the ecliptic plane, the Earth's axis, which once again is the imaginary line joining the north and south pole of the Earth, the axis of the Earth is tilted by 23.5 degrees relative to the perpendicular to the ecliptic plane. And so this tilt, amazingly, is what causes the Earth's seasons. The distance between the Earth and the sun is not the primary reason why we have seasons. All right, so let's try to understand why we have seasons. Okay, so the tilt of the rotation axis is responsible for the seasons. So here is another diagram of the Earth in orbit around the sun. Okay, now first of all, the orbit of the Earth is very circular. So in chapter 2, we are going to talk about what is the exact shape of the orbit of the Earth. It's not exactly a circle, but it's very close to a circle. So for a circle, you know that points on the circumference are at the same distance from the center. So the distance between the Earth and the sun does not change that much as the Earth goes around in its orbit, because the orbit is more or less circular. Okay. Now, suppose, let's start with this diagram, June 21st. Let's just call this A. So consider the Earth at location A, right? Which is more or less where the Earth is right now, because it's almost June. So at this location, the North Pole is tilted towards the sun, and the South Pole is tilted away from the sun, right? The tilt always stays the same, but the Earth is going around in its orbit like this. So sometimes the North Pole is tilted towards the sun, and at other times, the North Pole is pointed away from the sun, right? So that's what's happening at location A. The North Pole happens to be pointed towards the sun. So as a result of that, you can see that the Northern Hemisphere is getting more sunlight than the Southern Hemisphere, which is tilted away from the sun. So you can see that the Southern Hemisphere is mostly in the tilted away from the sun, and the Northern Hemisphere gets more sunlight than the Southern Hemisphere. In other words, there are more hours of daylight in the Northern Hemisphere than there are in the Southern Hemisphere, right? So also, so that is one reason why the Northern Hemisphere is warmer than the Southern Hemisphere. In other words, why it's summer in the Northern Hemisphere and winter in the Southern Hemisphere. One reason is that the Northern Hemisphere is tilted towards the sun, and so there are more hours of daylight in the Northern Hemisphere than there are in the Southern Hemisphere. Now, another reason is that in the Northern Hemisphere, you can see that the rays of light from the sun strike the northern points in the Northern Hemisphere more directly, whereas the same rays strike the points on the Southern Hemisphere more or less obliquely. So if you look at, that's made clearer in this diagram. So over here, the rays, you can see that the rays of light from the sun are striking the ground and the Northern Hemisphere more directly. They're coming in more directly. I can show that with my globe over here. Just imagine that the sun is right here, is to my right over here. So since and this is the North Pole, and it's tilted towards the sun, tilted towards my right. So the rays of light coming in from the sun are striking the North Pole more directly, right? Just imagine my fingers to be rays of light. They're striking the North Pole more directly. What about the South Pole? The South Pole is tilted away from the sun, so the rays of light from the sun are striking the South Pole more obliquely, because the South Pole is tilted away from the sun, whereas the North Pole is tilted towards the sun, so the rays of light strike the North Pole more directly. And that's what's indicated in these two diagrams at the top. In the North Pole, the rays of light strike more directly. And when the rays of light strike more directly, the energy of those rays is concentrated over a smaller area. And so you have more heating, right? Whereas when the rays of light strike more obliquely, then the energy is spread out over a larger area. And so you have you have less concentration of energy, and so you have less heating. Just imagine that you have one of those old-fashioned flashlights, big ones, which have, like something like this, very big, bulky flashlights. And suppose you shine it directly over a piece of paper. So then you're going to make a spot of light, right? So you're shining the flashlight directly over this piece of paper. So you're going to make this a spot of light directly underneath the sun, underneath the flashlight. And so here the rays of light are coming in more directly, and so the energy would be concentrated, right? Whereas suppose you do the same experiment, but this time you tilt the flashlight so that the rays hit more obliquely. So here is my flashlight. So now the rays of light are coming in like this. And so now you're going to get, they will form a larger, they will be distributed over a larger area, right? And as a result of that, the same energy would be spread out over a larger area if the rays of light are hitting obliquely. And so you will have less concentration of energy, and so you'll have less heating. So in this case, you'll have more heating. That's supposed to be more heating. And this case, you'll have less heating. And that's exactly what's happening. So as you can see, there are two reasons which are interrelated why it's summer in the Northern Hemisphere during June. And that is because the Northern Hemisphere is tilted towards the sun. And so there are two things that happen as a result of that. One is that there are more hours of daylight in the Northern Hemisphere because the Northern Hemisphere is tilted towards the sun. And the second is the rays of light from the sun hit the Northern Hemisphere more directly, right? Like this in the upper diagram over here. And as a result of that, the energy is more concentrated and you have more heating. So these two factors, more hours of daylight and the rays hitting more directly, are the reason why the Northern Hemisphere experiences summer. You can see that for the same reasons, the Southern Hemisphere is going to experience winter, because why? The Southern Hemisphere is tilted away from the sun, as you can see over here in location A. And so it has fewer hours of daylight because it's spending most of its time away from the sun. And also, the rays of light are hitting the Southern Hemisphere obliquely. And so it doesn't get heated up as much. And as a result of that, you have winter in the Southern Hemisphere. And that is why right now, it's summer in the Northern Hemisphere. But if you go to Australia or New Zealand, it's actually getting to be peak of winter. It's supposed to be, it's very, very cold in Australia and New Zealand. All right. Now, consider this situation. 6 months later, in December, let's call this location B. So the Earth is in location B in December, 6 months later. Now look at the Northern Hemisphere. The Northern Hemisphere is now tilted away from the sun. Remember that the direction of the tilt of the Earth's axis remains the same. So if this is the Earth's axis, initially it was like this, and then it rotated and it's like this. So now the Northern Hemisphere is tilted away from the sun. The Southern Hemisphere is tilted towards the sun, right? And so the same effect that I just described applies now to the Southern Hemisphere. So the Southern Hemisphere, points on the Southern Hemisphere are going to see more hours of daylight because the Southern Hemisphere is leaning towards the sun. And also the rays of light will be striking the Southern Hemisphere more directly. So the rays of light from the sun will strike the Southern Hemisphere more directly, whereas they will be striking the Northern Hemisphere more obliquely because the Northern Hemisphere is tilted away. And so for the same two reasons that we just discussed, the Southern Hemisphere will experience summer. It has experiencing more hours of daylight, and the rays of light from the sun, which also bring in heat, are also going to strike the points in the southern hemisphere more directly. And so it's going to be summer in the southern hemisphere and winter in the northern hemisphere, right? So December, it's hard for us, if you've never been to the southern hemisphere, it's a bit hard for us to imagine that when it's peak winter for us, like December, it's actually peak summer in Australia and New Zealand, and they have all these heat waves and forest fires and all that at that time. Okay, now there are two other locations, let's call them C and D. So that is in March and in September. So at that time, you can see that the direction of the tilt has not changed, but it's neither pointed towards the sun nor away from the sun. So just for a moment, I don't know if this is going to work, but suppose my head is the sun, right? And this is the Earth's axis. My pen is the Earth's axis. So right now, uh, this is the North Pole, this is the South Pole. The North Pole is pointed towards me, right? Um, and so in the Northern Hemisphere, it would be summer. 6 months later, basically it goes around. 6 months later, the North Pole is pointed away from the sun, which is my head. South Pole is pointed towards me, right? But when it's over here, now the North Pole is neither pointed towards me nor away from me, right? It's pointed in that direction, but the sun is over here. So the North Pole is not pointed towards me or away from me. And the same thing would happen when it's behind my head, behind the sun, like that, right? So the North Pole and the South Pole would neither be pointed towards or away from the sun. So at those locations, when the Earth is in these locations, then both the north and the southern hemisphere, northern and the southern hemispheres, get equal amounts of day and night, right? Okay, there's a beautiful animation of this, which I would highly recommend watching. So I'd highly recommend watching this video, and it's explained beautifully in this video. All right. Okay, now let's talk about the summer and the winter solstices. So the summer solstice is the one day when the North Pole is leaning closest towards the sun. So when the North Pole is pointed is leaning closest towards the sun, which actually happens on June 21st, that is um, called, excuse me, that is called summer solstice. And on that day in the Northern Hemisphere, you get the maximum hours of daylight on that particular day, because that is the one day on which the axis of the Earth is pointed closest towards the sun. You can see that over here. So in March, again, just imagine that my head is the sun. In March, the Earth is over here. I'm just showing the axis of the Earth. Just imagine the Earth surrounding this line. So in March, the Earth is not the axis of the Earth is not pointed either towards or away from the sun, right? But when the Earth moves over here, when it's in this location, then it's pointed maximally towards the North Pole is pointed maximally towards the sun, right? It's not so much pointed towards the sun over here, but when it gets over here, it's really pointed directly towards the sun, right? And so summer solstice is that one day when the North Pole is pointed closest towards the sun, and that is June 21st. And so on that day, you get equal amounts I mean, you get the greatest amount of sunlight in that day. And so you know that that is the longest day of the year in the Northern Hemisphere, right? Conversely, it's also the shortest day in the Southern Hemisphere, right? Now, winter solstice for us is when the North Pole is pointed most away from the sun. So that happens on December 21st, as you can see over here. In this, when the Earth is in this particular location in its orbit, which happens on December 21st, the North Pole is pointed most away from the sun. The South Pole is pointing most towards the sun on that particular day. So in the North Pole, that is the day of winter solstice, when you have the fewest number of hours of daylight. So you have that's the shortest day of the year. And then there are two other days. September 21st and March 21st, when the Earth's axis is neither pointing towards the sun nor away from the sun. So on those 2 days, you have equal amounts of day and night. And so those are called equinoxes. Equinox, nox means night. Equinox means equal amount of day and night, right? So that's why these are called equinoxes. So you have the vernal equinox on March 21st and the autumnal equinox on September 21st. All right. So hopefully it's clear to you why uh, how the tilt of the Earth's axis causes seasons. Now, to further drive home the point that seasons have nothing to do with the distance between the Earth and the sun, it actually turns out that when the Earth is in this location, when it's winter in the northern hemisphere, it's actually a little bit closer to the sun at that time, right? And when the Earth is in this location, the distance between the Earth and the sun is actually a little bit longer. So you can see that distance between the Earth and the sun really doesn't have anything to do with seasons. Seasons are caused entirely by the tilt of the Earth's axis. So please make sure that you understand this point. All right, let's move on to another topic. So I told you that the Earth's axis is always pointed towards the star Polaris. It's always pointed in a fixed direction, and that direction happens to be the star Polaris, which we also call the North Star. And I showed that over here in this diagram right here. I drew the Earth's axis as always pointing in the same direction. I mean, I didn't draw this, but in this diagram, it shows that the Earth's axis is always pointed in the same direction at all times as it's going around in its orbit, right? Now, that statement is not technically correct. The direction in which the Earth's axis points is actually not fixed. In fact, if you just imagine the Earth's axis, if you just imagine, just imagine the Earth's axis, which is this line coming out of the North Pole, going through the North and the South Poles, the Earth's axis actually wobbles like this. So let me just use my pen to indicate the Earth's axis. So right now it's pointed in this direction, but that is not fixed. Actually, the Earth's axis wobbles like this. This kind of motion, so it basically traces out a cone. The Earth's axis wobbles like this. So this kind of motion is called precession. So precession, so you might have seen this in a spinning top. The rotation axis of the Earth changes direction with time. And this kind of motion is called precession. Why does precession happen? That's way beyond the scope of this course. It's a physics phenomenon. It's way beyond the scope of this course. And we are not going to get into the physics of that at all. Okay, let me show you a demonstration of precession. All right, so this is a demonstration which I often show in class. So basically what's going to happen is, okay, I'll just let you watch it. So if you're absolutely flabbergasted by this, you are not alone. Every time I show this in class, I have a few students who always, their jaws drop when they see this. And this is another example of precession. So you can see that the axis of the bicycle wheel is not fixed. It's in fact, wobbling, right? So the axis of the bicycle wheel is wobbling. And so this wobbling motion is called precession. And amazingly, the same thing that's happening to this bicycle wheel right now is happening to the Earth. right? Uh, and so the axis of rotation of the Earth, as I was just mentioning, the axis of rotation of the Earth does the same thing. So it does not point in the same direction. It sort of traces out a cone like this as the Earth rotates. Now, so that is precession of the Earth's axis. How fast does it do that? The answer is it precesses very slowly by our standards. So it takes 26,000 years to complete one cycle of precession, which means that right now, let's say that it's pointed towards the star Polaris. Polaris is up there. So it's going to gradually trace out this cone, and then it will be back pointing in the same direction 26,000 years from now. So it precesses very, very slowly, right? Um, okay, so let me just pull up the PowerPoint again. All right, so very briefly, this is caused by the gravitational pulls of the moon and the sun on the Earth, but we are not going to get into the details of how this happens. And during a complete cycle of precession, the Earth axis traces out a cone, as I just mentioned. Oh, I think this is the same video that I just showed you. No. All right, so okay. So quick question, what is precession is caused by? See if you can answer this. It's just what I mentioned. So precession is caused by the gravitational pull of the moon and the sun. All right, now there's an interesting consequence of this. The consequence is that right now, our pole star is the star Polaris, right? So Polaris is our pole star, which means that the axis of the Earth points towards the star Polaris. However, as a result of precession, this was not always the case. In fact, so you can see easily why that is the case. So right now, the Earth's axis is pointed in this direction. Let's say it's the star Polaris, pointed towards the star Polaris. But since the Earth's axis is precessing, uh, thousands of years ago, it was pointed in a different direction, right? And thousands of years from now, it's going to be again pointed in a different direction. So Polaris is currently our pole star, but there is no, I mean, it's not going to be our pole star later, and it was not our pole star in the past. Interestingly, Egyptian records from 4,800 years ago show that there was a pole star at that time. People had noticed that there was a pole star, but from the way they describe the nearby stars, it's clear that they're not talking about Polaris. They're talking about another star, which is called Thuban. We can see Thuban in the sky pretty clearly. So Thuban happened to be the pole star about 5,000 years ago. So, and this diagram over here shows you uh, uh, the direction in which the Earth's axis would point as it precesses. So right now it's pointed in the direction of Polaris. 5,000 years ago, it was pointed towards the star Thuban, right? And so you can see that as time goes on, it's going to gradually keep changing direction. And 12,000 years from now, it will be in a completely, it will point in a completely different part of the sky, the star Vega, 12,000 years. I mean, the constellation Vega, 12,000 years from now. And 26,000 years later, it will again point towards Polaris. All right. So that is precession. All right. Now, let's talk a little bit about the motion of the moon. So the moon, as you know, is the brightest object in the sky. A question that I often ask in class, and see if you can answer this without looking down at the slide. Does the moon give off its own light, or does the moon not have any light of its own? The answer is the moon does not have any light of its own, right? The moon appears illuminated because it's simply reflecting the light from the sun. So the moon emits no light of its own. It simply reflects the light from the sun. And the moon revolves around the Earth. So if this is the Earth, this is the Earth, the moon revolves around the Earth, right? The time it takes to revolve around the Earth is 29.5 days. Now, I always get this number wrong, so let me just double check that. Somehow I can never remember the exact, I know it's around that, about 1 month, but I can never remember exactly what it is. So moon's period, I'm just Googling this. I have it wrong over here. I'll have to fix it in the slide. It's not 29.5 days. I always seem to think it's 29.5 days, but it's actually 27.3 days. Good thing I checked. All right. So the moon takes 27.3 days to rotate around the Earth. Now, you know that there are different phases of the moon, right? So yesterday, I believe, was full moon, or is it today? Yeah, yesterday was full moon. Today is just the day after full moon. It's called waning gibbous. Um, so the question is, why do we have these phases of the moon, right? Okay, let's try to understand why we have phases of the moon. The actual reason why we have phases of the moon is simply because different illuminations in its orbit give rise to different phases, or in other words, different parts of the moon appear to be illuminated to us because of where the moon is in its orbit. But the best way to explain this is by doing a little experiment, which I do in class, but I'll just show you a video of this experiment. So it's much easier for you to understand this if you just see this experiment rather than me trying to explain this in words. It's one of those things. It's much easier to understand by just watching. So I'll just show you this really nice video, and you can do this on your own. It doesn't take much equipment. All you need is a stick and a styrofoam ball and a lamp. That's all that you need to do this experiment. So if you have these, I'd recommend trying this out yourself. Okay, so I'll let you watch this.
Hi, my name is Emily Morgan, and I'm the author of Next Time You See the Moon from NSTA Kids. And I'd like to share a simple activity with you that can help you understand why the moon looks different at different times throughout the month. Why sometimes it looks like a banana, and other times it looks like half of a circle, and other times it looks like a big round ball. Well, to do this activity, you only need 4 simple things. You need a lamp with the shade removed, a white foam ball, a pencil, and a dark room. The darker the room, the better. Now in this model, the lamp is going to represent the sun, and of course the white foam ball is going to represent the moon, and your head is going to represent the earth. So let me show you how this works. We know that the moon orbits the earth. So in this model, I'm going to get the moon, the foam ball, to orbit the earth, my head. Notice that no matter where the moon is in its orbit, half of it is always lit up by the sun. But when the moon is in this position, I can't see any of the lighted side of the moon from Earth, my head. From this angle, you can see what I am seeing from Earth. We call this new moon. When it's new moon, we look up at the sky and we can't see the moon. It's there, but the side that's reflecting sunlight is away from us. Now, as I slowly make the moon orbit to my left, I can begin to see a tiny sliver of that lighted side. We call that a crescent moon. As the moon keeps orbiting, we can see more and more of that lighted side. We see half of the lighted half, which is a quarter moon. In this case, a first quarter moon. As we keep orbiting, we see almost the whole lighted side. We call that a gibbous moon. Then, when we can see the entire lighted half of the moon, that's a full moon. As the moon continues in its orbit, we begin to see less and less of that lighted side. We're back to a gibbous moon, but this time the light is on the opposite side. Then another quarter moon, last quarter moon to be exact. Another crescent, and finally back to new moon. And the cycle begins again.
All right, so hopefully it's clear to you why we have the phases of the moon. It just has to do with the position of the moon in its orbit and how much of it appears illuminated to us. All right. Oops. Okay, the next topic that we're going to briefly discuss is eclipses. So we had a spectacular solar eclipse in Nashville a couple of years ago, 2017. And so most of you have probably seen a solar eclipse. Let's just briefly discuss why we have eclipses. So as we just saw in the last video, I mean in the video that I just showed you, so here's the sun, and here is the Earth, and the moon is orbiting around the Earth, right? So this diagram obviously is not to scale. So the moon is orbiting around the Earth. Now, when the moon happens to be in this location, we call that new moon. And as the lady was explaining in the video, if you are on the dark side of the Earth, I mean the unlit hemisphere of the Earth, if you're standing over here at night, you will obviously not be able to see the moon at night because it's on the other side of the Earth. So it's new moon. All right. Now, when the moon is in this location right here, then it's full moon. And so now a person who's looking up at the sky at night will be able to see the moon, the face of the moon fully lit up, and that's full moon. All right, so that's new moon and full moon. Okay, now sometimes the following thing happens. So sometimes when the moon is in the new moon position and the sun, in other words, it's directly between the sun and the earth, then the shadow of the moon might fall on the earth. So that means somebody who's standing on the earth somewhere over here at this location might fall within the shadow of the moon. And so the view of the sun will be blocked for these people. So these people will see this black disk, which is really the moon, blocking the sun momentarily. And so that is called a solar eclipse. And as those of you that have seen the solar eclipse have realized, it's a pretty amazing sight. So the disk of the moon completely blocks the sun, and so it becomes dark, and it can get pitch dark. If it's a total solar eclipse, which means the sun is fully covered up, it can get pitch dark. And so that is a solar eclipse, when the moon is in between the sun and the earth, and the shadow of the moon falls on the earth. Now, what is a lunar eclipse? Lunar eclipse is very similar concept. So lunar eclipse is a similar concept. So what happens is that the lunar eclipse would happen when the moon is in full moon position, right? So the earth is directly between the moon and the sun. So now the shadow of the earth, I'll just draw the shadow of the earth like this. So this cone that I drew is just the shadow of the earth. The shadow of the earth might cover up the moon, or the moon might pass into the earth's shadow. So when that happens, whenever the moon passes into the earth's shadow, it appears that the moon is sort of suddenly, I mean, it's a full moon night, then the moon passes into the earth's shadow. So people watching from the earth would see this strange phenomenon where the moon seems to be disappearing or suddenly turning the full moon is suddenly turning something. It looks like something is eating up the full moon, and then the full moon is almost not visible, because it's entirely within the Earth's shadow, and then it emerges from the Earth's shadow. So it's not a quick phenomenon like the solar eclipse. It takes a little bit longer to happen, but you can watch the moon as it's slowly seems to be eaten up by something. You can actually see the Earth's shadow on the moon uh, gradually covering it up, and then the moon is fully covered up by the Earth's shadow, and then it emerges on the other side, and comes out of the Earth's shadow. So that is a lunar eclipse, and lunar eclipses happen a little more frequently than solar eclipses. So if you Google lunar eclipse, you might be able to find the date of the next lunar eclipse. All right, so that is a lunar eclipse. Now, one question is, okay, so this is what I was talking about regarding the solar eclipse. So during the solar eclipse, the moon passes directly in front of the sun, and so the part of the Earth where the solar eclipse is visible is in the moon's shadow, right? So the sun is completely covered up by the moon, and so at that time you can see depending on the solar eclipse, you might see um, this fuzzy region around the sun. And so this we'll see much later is the sun's outer atmosphere, and it's called the corona. So this fuzzy region that you see around the disk of the moon is basically the light that's coming from the outer atmosphere of the sun, and which is called the corona. So this is one opportunity that scientists have to observe the corona of the sun, because usually the light from the sun completely overwhelms all the light coming from the outer atmosphere of the sun. But during the solar eclipse, you have this one opportunity to observe the light coming from the corona. Sometimes the alignment between the Earth and between the moon and the sun is not perfect. And so you can have a partial solar eclipse. So you can have a situation where the moon's disk does not completely cover up the sun, and so part of the sun is still visible. And so this is called a partial eclipse. All right. Now, one question that you might have is that why, if this is really the situation, that the Earth and the uh, sun and the moon are like this, and when the moon gets between the Earth and the sun, you have a solar eclipse, and when the Earth gets between the sun and the moon, you have a lunar eclipse. So why don't we have a solar eclipse and a lunar eclipse every month? Because the moon takes 1 month to go around the Earth. So why isn't every new moon a solar eclipse and every full moon a lunar eclipse? The reason for that is the following. It's explained really nicely in this diagram from your textbook. So the reason is because the orbital plane of the moon is not is tilted a little bit to the orbital plane of the Earth. And what is the name of the orbital plane of the Earth? We discussed that earlier today. You should be able to answer it. What do we name that? What is this plane called? This plane is called the ecliptic plane. That's just the name given to it. It's the orbital plane of the Earth. So it turns out that the moon's orbital plane is tilted a little bit with respect to the ecliptic. So you can see the moon's orbital plane right here. That's the moon's, there's really no name for it. It's just, we just call it the moon's orbital plane. So the moon's orbital plane is tilted a little bit. And so as a result of that, most of the time, the moon's shadow misses the Earth. And that is why you don't get a solar eclipse every time you have a new moon. Like you can see in this situation right here, the moon's shadow misses the Earth, right? Also over here, the moon's shadow misses the Earth. So that's why you don't get a lunar eclipse, and you don't get a solar eclipse every time there is a new moon. Also, you don't get a lunar eclipse every time there is a full moon for the same reason. As you can see on the diagram on the, so over here, let's call this position B. So in position B, you can see that the Earth's shadow misses the moon. So the moon does not quite pass through the Earth's shadow when the Earth is in position B. In position A, which is this one, The Earth's shadow again misses the moon. So both the moon's shadow and the Earth's shadow miss each other. And so you don't get eclipses when the Earth is in these positions. You could get an eclipse when the Earth is in these positions, C and D, because here there is a chance that the moon's shadow might fall on the Earth or the Earth's shadow might fall on the moon. So that is why you don't always get a lunar eclipse or a solar eclipse every month. You only get them at certain times when the shadows of the moon and the Earth are land on each other. But usually they just miss each other. And that is because of the tilt of the moon's orbital plane relative to the Earth's orbital plane. Okay. All right, so you should be able to answer this question now. A total lunar eclipse occurs when? During which phase of the moon? Feel free to pause the video and see if you can answer this on your own. So a total lunar eclipse would mean we are talking about this situation when the moon passes into the Earth's shadow. So that would be during full moon phase, right? So the correct answer is during full moon phase. All right. The last thing that we are going to discuss in today's lecture is celestial coordinates. Now, this topic for some reason is not covered in your textbook. I don't know why, but I think it's an important topic if you're taking an introductory astronomy course. So I'll just briefly discuss what celestial coordinates are. Now, celestial coordinates give you a way of locating an object in the sky, right? I briefly mentioned one way of locating an object in the sky in the previous lecture. I told you that there is the celestial sphere has these constellations on it, right? So the sky has been basically divided into these constellations, and each constellation is a particular region in the sky. And so you can just mention a particular constellation. So you can say that, okay, I saw this interesting object in the direction of the constellation Sagittarius. Now, that would give me, if somebody told me that, I would know what direction they're talking about, because I know where the constellation Sagittarius is in the sky. But that's a large region of the sky, right? You need something more precise to pinpoint an object in a particular location of the sky. So for that, we need celestial coordinates. So using constellations, you can just point to a general part of the sky, but if you want to really pin, it's like saying that so and so person lives somewhere in Texas, so you know which part of the United States they live in. But if you want to pinpoint exactly where they are, you need their address, their street address, right? You need something more precise. So that is what celestial coordinates do for us. They give us a way of pointing precisely to a particular part of the sky, right? Now, there are two systems of celestial coordinates. The two systems of celestial coordinates are the system of right ascension and declination, and azimuth altitude azimuth. So this second one is sometimes called the alt-az system for short. Alt stands for altitude and az stands for azimuth. And right ascension and declination is sometimes, for short, people just call it RA/dec. That's just a short name for it. So I'll explain what these are. Now, let's start with right ascension and declination. So right ascension and declination give you a set of coordinates with which you can locate any object in the sky. And in spirit, these are very similar to latitude and longitude. So let's just quickly review how latitude and longitude work. So you know latitude and longitude, right? So you know that there are all these circles which are drawn on the globe. This circle which passes through this around the center like this is called the equator. And then you have these smaller circles. So you have another one that's going around like this, and then another one that's going around like this, and another one that's going around like this. And then also below the equator, you have these smaller circles. So those are called the lines of latitude. So those smaller circles are the lines of latitude. In our diagram over here, you can see the equator right here. It's this one. And then you have, here is an example of a line of latitude. It goes around, obviously, on the other side as well. Here is another line of latitude, right? And here is another line of latitude. So these are the lines of latitude. Okay, the equator is 0 degrees latitude. And then as you go further up, you just measure what angle this is. So if this is the center of the Earth, the equator is 0 degrees. This line of latitude might be at 45 degrees or something. So this is called 45-degree latitude. And this line of latitude, the other one that I've drawn, might be at 60 degrees or something like that. So maybe this angle is 60 degrees. So this is 60-degree latitude. So that's how the lines are named, 60-degree latitude. What is the latitude of Nashville? Let me just look it up. I can never remember that. Latitude of Nashville. The latitude of Nashville is 36 degrees. So 36 degrees latitude is where we are. All right, so anyway, so these are the lines of latitude. What latitude would the North Pole have? Can you answer that based on this? So so you would draw this line, right? What angle is that making? So that's 90-degree angle. So the North Pole would be 90 degrees latitude. So this is how you can get the latitudes in the northern hemisphere. What about the southern hemisphere? So you do the same exact thing, but you just use negative angles to indicate that you're in the southern hemisphere. So for example, this angle would be the same, whatever this angle is, this one right here. Let me just get rid of, let's make this a little cleaner. So for the southern hemisphere, so this is our equator. So if you draw this line and then find out this angle right here to get the latitude of this line. So whatever this angle is, I don't know what it is, maybe 40 degrees or something. So you just say that it's minus 40 degrees to indicate that it's in the southern hemisphere. Or instead of saying minus 40 degrees, you can also say south latitude. So these are these lines are north latitude. And these lines over here below the equator are south latitude, right? So so that's instead of a negative angle, you can say that this is south latitude. That's also another convention. So that is how you, so this line would be 40 degrees south latitude, right? And this line over here, I had said earlier, was some 45 degrees or something. I'm just making up these numbers, 45 degrees. So these would be north latitudes. This would be 60 degrees north latitude. All right, so that is how you get the latitude, how you get the latitudes. What about the longitudes? It's the same thing, except that the longitude circles all pass through the North Pole and the South Pole. So here is one line of longitude. Here is another circle of longitude. So if you take a look at a globe, the latitude circles are parallel to the equator, but the longitude circles all pass through both the North Pole and the South Pole. So they're all the same size, and they pass through both the North and the South Poles. So here are some more lines of longitude. Okay. All right, so that is the system of latitude and longitude. And how would you use latitude and longitude to indicate the location of a place? So suppose you want to find the location of, let me just clear up my diagram again. Suppose you want to find the location of this point, then to find this location, you need to specify what line of latitude is passing through that point and which line of longitude happens to be passing through that point. Once those two are known, you can immediately figure out that location, right? So that is how you locate points on the Earth using latitude and longitude. All right, now right ascension and declination is a system which is very similar to that, except that instead of using the Earth, you use the celestial sphere. So I told you that the celestial sphere is this imaginary dome or large sphere that surrounds the Earth, right? And it looks like all the constellations and stars are painted on the celestial sphere. So the celestial sphere is this imaginary dome. It's basically the sky, the whole sky, right? Um, so suppose here is the Earth in the center of this diagram, and here is the celestial sphere. It's the imaginary dome that surrounds the whole Earth. It's basically the whole sky. So suppose you extend the lines of latitude and longitude onto the celestial sphere. So here is the Earth's equator somewhere over here, right? Suppose you project that onto the celestial sphere, then you get what is called the celestial equator. So the celestial equator is basically the projection of the Earth's equator onto the celestial sphere. And so you can do the same thing with the lines of latitude. So here is a line of latitude on the Earth. If you project that line of latitude, you might get this line on the celestial sphere, right? So when you project the lines of latitude onto the celestial sphere, the lines that you get are called the lines of declination. So these are the lines of declination. So the lines of declination are analogous to the lines of latitude that you see on the Earth. All right. Okay. And they are indicated by angles, just like you indicate the angles, indicate the lines of latitude by angles. You can also indicate the lines of declination by angles. Now, I told you that the lines of latitude for the Earth, the lines of latitude in the northern hemisphere, you just indicate that by saying, putting an N next to it. So you say Nashville, for example, is as 36 degrees latitude north, indicating that it's 36 degrees latitude in the northern hemisphere. And in the southern hemisphere, you would do 36 degrees latitude south. I mean, for whatever latitude it is, you'd put a south. For declination, instead of saying north and south, you use positive and negative angles. So you would say 45 degrees, positive 45 degrees declination to indicate a point in the northern hemisphere, and negative 45 degrees declination to indicate a point in the southern hemisphere. So if this declination happens to be at an angle of what would it be? Maybe 45 degrees. So you would say it's plus 45 degrees declination over here. And this one, which happens to be below the equator, below the celestial equator, would be minus 45 degrees declination. So instead of using north and south, you just use positive or negative angles, right? And I probably mentioned this, but this line, which is this circle, which is the projection of the equator, is called the celestial equator. All right. So hopefully it's clear to you what is the celestial equator. It's the projection of the Earth's equator onto the celestial sphere. What are the lines of declination? So they are the projection of the lines of latitude onto the celestial sphere. And so in the northern hemisphere, the projection of the northern lines of latitude, you indicate with positive angles, and the projections of the southern lines of latitude you indicate with negative angles, right? Now, what do you think is the declination of this point? Let me just name this point first. So the Earth's north pole is over here. The north pole of the Earth is over here, and the south pole of the Earth is over here. And so this line is the Earth's axis of rotation, right? If you project this line onto the celestial sphere, then this point which is the projection of the Earth's north pole, is called the north celestial point, and this north celestial pole, and this point is called the south celestial pole, right? So the north and south celestial poles are, if you just project the Earth's axis So the point where it meets the celestial sphere will be called the north celestial pole. And if you project the Earth's axis this way, this is the south pole. If you project the Earth's axis this way, the point where it meets the celestial sphere will be the south celestial pole, right? Okay, so can you tell me what is the uh, okay, let me just ask you a simple question. What is the latitude of, on the Earth, what is the latitude of the North Pole? So what latitude would that be? The answer is it would be 90 degrees, right? So because the North Pole makes a 90-degree angle. So it would be 90 degrees north. And what is the latitude of the South Pole? It would be 90 degrees south, right? Because for Earth, we use north and south to indicate the north and the south hemispheres. Now, can you tell me what is the declination of the north celestial pole? The declination, remember, declination is very similar to latitude, right? So what is the declination of the north celestial pole? The answer is 90 degrees, but how do you indicate that it's the north celestial pole? So there the convention is to just use a positive angle. So plus 90 degrees would be the declination of the north celestial pole, and minus 90 degrees would be the declination of the south celestial pole, right? So that is declination. Now, we can't just use declination to indicate objects in the sky. We need the analog of longitude as well, right? So longitude, lines of longitude are, again, are circles which pass through the north and the south poles. So you have the same thing for the celestial sphere as well. So these circles which pass through the north celestial pole and the south celestial pole, like here's one of them, here is another one. These circles are called lines of right ascension. They're called lines of right ascension. So lines of right ascension, as you can see, are very analogous to lines of longitude. In fact, they're obtained by just projecting the lines of longitude onto the celestial sphere. So right ascension, the lines of right ascension are the projection of the lines of longitude onto the celestial sphere. And the lines of declination, as we just discussed, is the projection of the lines of latitude to the celestial sphere. Okay. All right. And so what do we measure the lines of right ascension in? We could have measured them in degrees, but we don't. There's a different way of measuring them. It's a little bit easier than degrees. It is to just use hours, just like the hours of a clock, right? So you know that for a clock, this could be this could be 12 or 0, and then this is 1 o'clock, this is 2 o'clock, and 3 o'clock, 4 o'clock, 5 o'clock, 6 o'clock, like this, right? So you can denote directions using hours, right? Sometimes that's done like sometimes you'll say that somebody is directly on your 6, so that means directly behind you, 6 o'clock, right? So you imagine this clock dial, 0 is directly ahead, 6 would be directly behind, and so on. 3 would be to your right, and so on. So the lines of right ascension are measured using hours. So this line is 0 degrees right ascension. This one might be 5 degrees, 0 hours right ascension. It's not degrees, it's hours. So this one might be 5 hours right ascension. This one might be 10 hours right ascension, and so on. And so it's like that. So 0 and then 5, 10, or whatever, and it just goes all around until it comes to, actually this is not going to be 5. So there are So it's 0, and then it keeps on increasing. And when it comes all the way around, it's 24. So it's just like a clock. So 24 hours means you've gone full circle. So the lines of right ascension start at 0 and then go all the way around until they come back to 24. And so 24-hour right ascension is the same thing as 0 hours right ascension. Just like if you go 24 hours on a clock, you come back to where you started. The dial comes back to where it started. So instead of measuring the right ascension in degrees, in which case it would just go from 0 to 360 degrees, the convention is to just measure it in hours, where it goes from 0 to 24 hours, with 24 hours meaning it's come back to where it started. So that is how you measure the location of an object using right ascension and declination. So you specify the declination that gives you, let me just clear up the clutter over here. So you specify the declination on the celestial sphere. So that would be one of these lines. And you specify the right ascension. So that might be this one, this circle. And so the place where the right ascension and the declination intersect is the location of the object. So that is the right ascension declination system. And as I clarified, it's exactly analogous to the latitude and longitude system, except that you're doing it on the celestial sphere rather than on the Earth. Now, there is the other system for calculating altitude. The other system for locating an object in the sky is called the altitude azimuth system, or as I said, it's also called the alt-az system. So how does the alt-az system work? The alt-az system is very simple. So it is really based on where you are. So your alt-az of something is not going to be the same as somebody else's alt-az. So the way alt-az works, first let's start with altitude. So actually, let's start with azimuth. That's probably easier. So suppose you are pointing directly towards the north. So let's say that towards the screen, towards my screen, where my finger is pointing right now, is due north, right? So that is called 0 degrees azimuth. Now, if I rotate my arm so that it's pointing towards the east, that would be 90 degrees azimuth. If I rotate it all the way back so that it's pointing towards the south, that would be 180 degrees azimuth. So you can see that in this diagram over here. Due north is 0 degrees azimuth, east is 90 degrees azimuth, south is 180 degrees azimuth, west would be 270 degrees azimuth. And then if you go another 90 degrees, you're pointing north again. So you'd have gone a whole 360 degrees. And 360 degrees, if you go a whole 360 degrees, you're again pointing in the same direction. So 360 degrees azimuth is the same thing as 0 degrees azimuth, right? So that is how you can indicate the direction of an object. But you also need to indicate how high it is in the sky, right? So you also need to you have to point out what direction it is and also how high it is in the sky. So for that, you use the altitude. Altitude works in a very similar way. 0 degrees altitude means that it's level with the horizon. 0 degrees altitude means it's at the level of the horizon, right? Then as you point higher, like this point, this direction would be 20 degrees altitude. This direction would be 45 degrees altitude. This would be 70 degrees altitude. And if you're pointing straight up, that is 90 degrees altitude. So the point directly above your head is 90 degrees altitude, and another name for it is the zenith. So your zenith is directly above your head right now, right? And the point that's directly underneath you, this direction, is called your nadir, though we are not going to use the nadir very much. Okay, so hopefully the altitude is clear. So altitude 0 means that it's on the horizon, it's at the level of the horizon, and then you can increase the angle to indicate, then you can indicate what angle an object is, and give its altitude. All right, so using the azimuth and the altitude, you can figure out, you can locate an object in the in the sky. But notice one thing: the altitude azimuth system really depends on where you are. So suppose you're talking about suppose you're in Nashville, which is right here. Suppose you're in Nashville, right? And you are pointing directly upwards. So you are pointing towards 90 degrees altitude. So that would be in this direction, right? Would that be the same for a person who lives in Australia or in Africa? So for them, if they're pointing directly upwards, it's going to be this direction, right? So your altitude 90 degrees is not the same as the altitude 90 degree of somebody. I mean, the altitude 90 degree of somebody who's living in Africa is not the same as the altitude 90 degree of somebody who's living in the northern hemisphere in Nashville. So you can see that altitude and azimuth really only depend are very dependent on the location of the observer. So that is a drawback of this system. The right ascension declination system is the same for everybody. It has nothing to do with a particular observer's location on the Earth. So this is the same for everybody. So if you want to communicate your location, so suppose you see something interesting in the sky, and you live in Nashville, and you see something interesting in the sky, and you want to tell your friend who lives in India about that, right? So which system are you going to use to indicate so that the person in India knows where to look in the sky? So are you going to use the altitude azimuth system, or are you going to use the right ascension declination system? So the altitude azimuth system would not be useful, because your altitude azimuth where you are would be meaningless to somebody who's at a different location, right? So so you should use the right ascension declination system. Okay. Here is an example problem. Which of the following are the coordinates of a star that's setting in the northwest? So feel free to pause the video and see if you can answer this, and you can take help from this diagram. So you have a star that's setting in the northwest. So what would be the altitude and azimuth of that star as it's setting in the northwest direction? So looking at the answer choices, okay, I'm assuming that you paused the video and thought about this for a little bit and have come up with an answer yourself. The correct answer is this one. So why is that? First of all, the star is setting, right? Which means it's level with the horizon. It's about to go below the horizon. So what altitude is that? So when an object is level with the horizon, that's altitude 0 degrees, right? Now, which direction is the star? The star is in the northwest. So this is north and this is west. So northwest would be this part of the sky, right? And so, or this direction. So 300 degrees would be in the northwest, right? And so, so the correct answer, looking at all these answer choices, the correct answer would be azimuth 300 degrees, altitude 0 degrees. None of the other answer choices would make sense. Okay. All right, so that is the azimuth altitude system. And we just have one brief topic left in chapter 1, which we will finish next week.